Okay, so I have prepared like small introduction. So previously we were working with tables like table like this. We were working with Pokemon because this is like the domain that everyone is expert. So there's no need to explain the domain. But long story short, we had a table like this, which hold information about the Pokemon. So they have a name, they have some statistics. And just one more step. Does anyone know what Pokemon is? I mean, it doesn't really matter, but it's just about some dogfights, more or less, right? Yeah. So we had table like this, and in previous presentation we were focusing on normalizing data, and at the end of it we have finished with data like this, which was beautifully normalized. But today we'll be looking at just this one table here. So the story is we arrived to the project, we have inherited it, standard legacy thing, and we got what we got, the Pokemon's table, and our our project manager or whoever have given us new task or new business requirement, right? So he's like, okay, look, so our interns has gathered some data, you have to put this data into the table. Okay, let's do it. So this is our table, and let's put some data in it. So yeah, I have been doing this long time, so now you have to watch it. Whoa. And even more. By the way, here at the meeting there was one presentation, really cool one about backfilling, but in our case backfilling is super simple, we're just adding some data. For some reason, we have just 32 of records, and our Pokemon table looks like this. So yeah, we have staggering amount of Pokemons, 32, but it's just enough to figure out some behavior with it. So yeah, we have done it, we have closed the ticket, great success, but then our project manager come back to us and say, wait, this doesn't work, it's slow, when we are looking through the table and looking for the Pokemons, and we're trying to find them by the name, it's slow. The customers are very angry and they're closing the subscriptions. Money. We need to make more money. Just make it faster so we don't lose customers. Okay, so it's time for debug. Well, let's see what's going on. So let's pick a random Pokemon. We'll pick this one because why not? And let's try to find it. So we were checking, okay, the first one, okay, it doesn't look like this, so let's go more and more and more. Okay, here it is. So it wasn't that bad. We have found it really fast. So we decided that maybe this debug is not that great, right? So let's find another Pokemon. This time, this one. And again, we have no other way to find this Pokemon, so we are going through the whole table, and this is my time for a sip of beer. Because again, I spent so much time on animating this, so you have to watch it. Okay, and here it is. We have found Kadabra, and we have confirmed, okay, it doesn't work that fast. So the further the Pokemon is in the table, the longer it takes. Okay, we found a bug. Now it's time to fix it. But fortunately, we are in the world of Pokemon, and we have an arbor plot. So our table has just evolved. And from this, we ended up with something like this. And our Pokemons are nicely sorted by names, right? And we remember something from the studies or courses or Coursera or whatever, that finding record in sorted table is much easier, right? Because we can go and find Charmeleon in this table. So we can go in the middle, and since it's sorted, we know that M is far away than C, so everything above we can leave, and everything which is below we can discard, right? Now let's go to the middle as well. Okay, so Charizard, this is not so easy because there are so many similar letters, but I believe Charizard is before Charmeleon, so we'll go like this, and so on, until we find our record. It's great success because by sorting the table we have allowed us to speed up the searches really fast. It doesn't really depend how far from the beginning it is. So again, great success. We closed the ticket. But then our TM came back to us and say, you know what? This is great that you fixed this one, but you have just broken finding by IDs. What's going on? So Welcome to our presentation. Yeah, so my name is Mateusz, and we'll be talking about we'll be talking about the indexes that struck us back, like in the second part of trilogy, because maybe somewhere there will be third part of the Pokedex trilogy. Anyways, first thing we need to do is to figure out what we have broken, and we already know this, because by fixing the names, we completely messed up the order of IDs, right? So now finding by IDs, we have the very same problem we had with the names before. Simple. So what do we need to do? Revert the changes and push to production. And we need to go a bit deeper and understand what the hell has just happened, why we broke it, right? Because again, this is the legacy code we inherited. We don't really know what's going on, and it turned out that, yeah, we made some wrong assumptions and simply broke it. Okay, so let's go back to our table. And it's turned out it's not the table, because it is, wait for it, this is B tree, which stands for, anyone?
Binary tree.
No, not binary tree. I just forgot it. We'll get back to it. It's not binary tree, it's the another one. And, come again? No, okay. Balance tree, yes, thank you so much, too much beer. Okay, and yeah, we did some digging around the documentation and so on, and it turns out that someone thought like this. The keeping information about index is taking like additional space, so let's use an index which is holding all the information about all the records, right? So it is indexed by the IDs, and this tree has leaves, obviously, like each tree. It has some branches over here, and it has the root. So we'll keep digging and trying to understand what's going on here. So let's find some Pokemon by ID, 7. And how it is organized, it's those numbers are showing what is the biggest value of index in each of the leaves, right? So we have like, we have like 4, which is corresponding to here, 8 here, 12 here, 16 here, and so on and so on. And for the sake of readability, here we have just two values, here also we have just 2 values and 2, but those can be like, they can have much more, like 2, 3, 4, whatever. And in the end, we have like small chunk of our data that we'll be traversing through. Okay, so we're starting at the root, obviously, and we're saying, okay, 8 is bigger than 7, so this is the way we should go, because everything below 8 is this way. So let's go to the branch. We see, okay, 4 is like below 7, so this is not the way to go, because it's saying basically all the leaves with ID lower than 4 are this way. So we have 7, which is bigger, then we are going to another one, which is showing us the way to those leaves. And those leaves are like linked list or whatever, so we'll be basically going one by one in them. But there's so many of them, it can be 4, it can be 100, it can be whatever, but it will be much faster to transverse from it. So we are going and, hey, here it is. Here's our Pokemon with the ID 7. The only thing we need to check is like the one record afterwards, because if we'll be like finding by names or whatever, then can be multiple Pokemons named the same for some reason or whatever. But yeah, this is basically how we work with the B tree. And like I said, someone has decided that let's use index to keep all the data. And situation like this is called index organized table. And it has one more cool feature, because yeah. Okay, so here are the numbers that are abstracted. Let me move this a little bit. Maybe Mariusz won't be angry. Okay, so those numbers in blue are representing like physical addresses on disk, because we have to store data somewhere, right? And they have to be stored somewhere physically. So these are the addresses. They're like arbitrary numbers, doesn't mean anything. There's some like places on the disk that we are storing it. And someone thought that, hey, if our records will be scattered around, it will be quite hard to find like the group of them, right? Oh, for example, we want, for some reason, to get all the Pokemons which has ID 5 to 8, those. And it turns out that they are scattered all around the disk. What if we do something like this? And so the records that are in our table are also next to each other on our disk drive, right? And what benefit do we get? Because when we will be, like, again, reading for the block of data, we'll be getting them from one place, and this probably will mean less reads from the disk, because, like I said, if it's all around the place, we'll have to do, I don't know, 4 reads or 5 or whatever. And in this case, we can do 1 or 2. It will be faster, more efficient, and cooler, right? Okay, so yeah, we dig into deeper. We finally understand what's going on with our table that we were working with. It's time to go back to business and fix this ticket, because yeah, they're still calling us that it's 2 days and we haven't done any commit, so it's time to do some work, right? Okay, so this is our table, and we are interested actually only in this part, right? We want to know what the name is and what the ID of the Pokemon is. So we'll take it and sort it, just like we did already earlier. So we have nice index right now, which says, okay, Abra has ID, this is the ID. Arbor, it's this ID, and so on and so on. It's sorted, so we can, yeah, fast something in it really fast. It obviously looks like this, so it's again B3, and we can find, yeah, Pokemons by names really fast. We know how it works. Great success. So yeah, let's go to this view. And it's called, yeah, secondary index, because we are creating like another data structure that is telling us how we can find the Pokemons organized by names. Okay, now our PM comes to us and say, look, you know what, this is too slow because finding by names, okay, it's faster than it was, but it's still not as fast as I want to be. We are still losing customers, you know, it cannot be like this. Do something about it. Okay, so it's time for debug. So we have our names index and our main table, which is index, and we're trying to find the Charmeleon. And we know how it looks. We have to do the tree transversal in here and find out the information that it has index 4, but we cannot say, and okay, here is 4. We have to find it in this, right? So we have to make another tree transversal, go through the whole tree to find where the 4 is. So it turns out that in order to find the Pokemon by name, we actually have to make 2 searches, right? First we are searching one table, and then at the end this table is saying, okay, this is the ID of your Pokemon, and then we are going to another table sorted by IDs, and we have to go through it and do the search. But we have a brilliant idea. We know that those records has some row ID or like identifier where it lays like in the physical world. So what if instead of having index, we'll use those values, and then it will be like, hey, where is the Charmeleon? We'll do the search in this index, and then we'll say, okay, here it is, straight away, without finding the record, doing the search in second one. And this turns out to be a great success, because it's working, there's only one search needed, and finally the PM is happy. But of course, he brings more stuff. So he's saying, okay, this works great, so this is the time to add new Pokemon to the table. So yeah, it's not that bad, we can do it. We are lucky because our table is organized by IDs, so we can go to the very bottom of the table. We don't care about the order, we just add another record, add at the very end of it. So here it is, we just added the new record. But we remember that we have a second structure here, names index, and we have to add it here, but this is sorted, right? So we want to have it to be sorted after the insertions as well. So again, we are going here, and turns out that we'll need to add this Pokemon somewhere around here. So let's do it. Here is new Pokemon, and if you noticed or not, we also changed this one, which is at the very end of the leaves. So this also had to be changed, and this also had to be changed. So it turns out that adding data to our table needs some additional steps to be done, like with the indexes. It's additional cost, but we can live with it. The B tree is well documented. There are plenty of algorithms around the internet that are explaining us how to do it. Okay, we can live with it. We have done it. And this is how it looks, our table after the insertion. It's like after Metapod and before knee-docking, so it's where it should be. It holds the information where it's stored on the physical space. So again, great success. And of course, as a reward, we are getting new business requirement. This time, we are supposed to remove Pokemons from the table. Okay, for some reason, I don't know, maybe they are extinct or whatever. So it turns out we need to get rid of those two for some reason. We don't really care, we just got the IDs. Okay, so let's remove them. But this time, it turns out that it's not so simple, because as you remember, the idea of this table is that the records are next to each other. So we cannot simply leave the free space here because it would be like unusable, right? We need to move those records and change where they are stored over here. And this is like quite costly, right? Because look, we have Pokemon number 15 over here, and there are 32 of them. And it turns out that we need to change the addresses of the Pokemons for half of the table. And yeah, if we would be changing here, it would be turn out that we'll need to change everything. But on top of this, we also need to change the values of those indexes here, like of 16 of them. So it turns out that current data structure is not really working with the deletion, because it will make it super inefficient and require a lot of additional like overhead or whatever. The cost will be just great. So we need to fix it. But fortunately, our table is evolving again, hopefully in the right direction right now. So what happens now is our table is changing into our table again, but now it has separate index for IDs. And what has happened now is, not sure if it's super visible, but those numbers are like, looks random now. So long story short is that we no longer care that next records are next to each other. We simply put whenever there is a place, and situation like this, table like this is called hash table. So whenever there is a free space, we're just putting it and adding IDs to our index. And in this case, yeah, in heap table, data is stored statically. So when we are deleting something or inserting, we don't rearrange the table. We are losing this ability to pull like a bunch of data at once, which was really cool at the very first of our journey. But right now it turned out to be so big blocker that we don't want to do it anymore. Okay, so let's see if we now can do the deletion. And it turns out that it's super simple, because we just go to our table, we are deleting it and forgetting about it, right? We don't care, we don't need to readdress all of this. Yeah, the addresses of it hasn't changed. Same thing applies to our indexes, right? Let's find our records here. Don't know why it jumped, but never mind. Here and here, just delete it. No rewrites needed, nothing. We will just rearrange our tables, but B trees, but it's doable. It's not that painful. So yeah, let's try insertion and search if it's working. So let's assume that we need to add this Pokemon with ID 16 that we have. So what we're gonna do? We're going simply to the very end, add Pokemon with ID 16, because they said, you know what, they're not really extinct, just put them back. So we're putting them here at the end. We don't care about the order inside the table, because what's holding information, how the indexes are organized, which are no longer here in order, is our index, IDs index. And yeah, insert there in the right place, and also insert there whenever it's fitting, like the animations we were showing. And I think that's pretty much it from what I had to tell. So now is the time for the question. Just a brief reminder that my GitHub account is from 2016, but my IMDb is since 2011, so thank you.
Why you are inserted the last records with the same IDs?
Come again, yeah?
Why you inserted these two Pokemons that you previously deleted with the same IDs?
I mean, it was just to show that they doesn't have to be in order.
Okay.
It was just to illustrate, because normally we would use like additional ID, but it was just to show that we no longer have to have them ordered, because index on ID, it's like quite special case when we are like incrementing it every time we're adding. So it's just for the presentation purposes that it works nicely without it. So yeah, long story short, it's like almost non-databases is really using this index organized table, because it works nicely when we have one index, like we saw with the IDs and everything. But if we were trying to add additional index, it's trying to too much convolute.
Yeah, because from like real database perspective, the primary index is the index based on that the data is stored, so it should be kind of sorted.
But at the same time, you can use UUID as your ID for, and UUID is never sorted.
Yeah. Depending on the version.
Yeah, depending on the version, exactly.
All right, so thank you. Then that's it.